All right, welcome. Have you ever really thought about what's going on between the whole numbers on a ruler? Like between 1 and 2? Well, today we're going to dive right into that world. We're talking about rational numbers, the very architecture of how we think about fractions and really parts of anything.
So here's our game plan. First, we'll figure out why we even need these numbers in the first place. Then we'll get a solid definition for them. After that, we'll see how they play together. The rules for adding, subtracting, and multiplying. And finally, we'll actually map them out and see where they all live.
Okay, so let's jump in, and the best place to start is actually with the numbers we're already super familiar with, just to see where they start to fall apart.
And that brings us to a really simple, but honestly a pretty deep question. Why aren't our basic counting numbers, 1, 2, 3, and so on, why aren't they enough? What's missing from the picture?
Think about how our number system kind of grew up, right? First, we had the natural numbers, just for counting stuff. Then we realized we needed a zero, so boom, we got whole numbers. Then we needed negatives, and that gave us the integers. But even with all that, there's still this massive gaping hole. What about all the stuff in between those integers?
Well, that is where rational numbers come in. They are this brilliant system that was basically invented to fill that gap, to handle all those parts of a whole. Things like half a pizza or a quarter of a mile.
And here it is. This is the big one, the fundamental rule of the game. A rational number is just any number you can write as a fraction, p over q, where p and q are both integers and, this is the important part, q, the bottom number, can't be 0. Seriously, this one definition is the key that unlocks this entire topic.
So here's a really crucial point. This new system, the rational numbers, it doesn't just throw out the old numbers we knew. No, it actually includes them. It's like a bigger box that holds all the smaller boxes. Every single integer, take the number 5 for example, is also a rational number. Why? Because you can just write it as 5 over 1. See? This system just expands our whole mathematical universe.
All right, so we know what they are. Now let's find out how they behave in the wild. What happens when we try to add and subtract them? Well, it turns out they follow some really clear, almost elegant rules.
So the first big rule for addition is something called the commutative property. And yeah, it's a fancy word, but the idea behind it is super simple. Order just doesn't matter. We all know 2 plus 3 is the same as 3 plus 2. Well, guess what? The exact same thing is true for fractions.
And this is how it looks in the language of math. It's basically saying you can take any two fractions, add them up, and then you can flip their positions, and you are guaranteed to get the exact same answer, every single time.
And here's a perfect example of that property in action. Look at these numbers. Whether you start with the negative 7 over 12 or the positive 5 over 8, once you do the work, find that common denominator and add them up, you land on the exact same answer, 1 over 24. Pretty cool, right?
Okay, next up is another big one, the associative property. And this one is all about grouping. If you've got a whole list of numbers to add, it literally doesn't matter which pair you decide to add up first. The final answer is already locked in. And this is where it gets really interesting. Seeing this principle at work, you could group the first two fractions, or you could group the last two. Now, the steps you take in the middle might look a little different, but that final answer, it's going to be 5 over 12, no matter what. And that's actually a super powerful tool when you're trying to simplify complicated problems. So when it's time to actually do the addition, there's a reliable 4-step recipe we can always follow. First, you've got to make those bottom numbers, the denominators, the same. You do that by finding the LCM. Then you adjust the top numbers to match. After that, just add the tops together, and for the last step, simplify the whole thing if you can.
But, and this is a really critical distinction, subtraction is a bit of a rebel. It doesn't play by all the same rules. This comparison makes it super clear. Now, both addition and subtraction have something called closure, which is just a fancy way of saying you'll always get another rational number as your answer. But look at this. Subtraction is not commutative, and it's not associative. We all know 5 minus 3 is definitely not the same as 3 minus 5. Order matters a whole lot with subtraction.
Okay, so let's switch gears and talk about multiplication. And the good news is, multiplication behaves a lot more like addition. It follows a really consistent, really predictable set of rules, which makes it an incredibly powerful operation to have in our toolkit. So multiplication pretty much ticks all the same boxes as addition. It's got closure, it's commutative, and it's associative. But it also has a couple of its own special tricks. There's the multiplicative identity, which is just the number 1.
And then there's the multiplicative inverse, or what we usually call a reciprocal, which exists for every single number, except 1.
And that one exception is the number 0. This is a crucial one to remember. You just can't find a reciprocal for 0. I mean, think about it. You can't just flip 0, which is like 0 over 1, to get 1 over 0. Because we all know dividing by 0 is a huge no-no in math. It's undefined. 0 is the one number that just breaks that pattern.
All right, for our final piece, let's actually try to visualize where all these fractions live. Because when we start to map them out on the number line, we uncover one of their most, well, mind-bending and honestly beautiful properties.
Let's start with a really simple task. We've got the number 7 and we've got the number 8. We know them well. But what's actually hiding in that space between them? How would you go about finding just one number that fits perfectly in that gap?
Well, the method couldn't be simpler. All you have to do is take your two numbers and find their average. Just add them together and divide by 2.
And for 7 and 8, that average is, of course, 7.5. And there it is, sitting perfectly in the middle. It's a rational number, filling that space between two integers.
Okay, but here's where things get truly wild. Because what's stopping us from taking the average of 7 and our new number, 7.5? Nothing! And we could do it again and again forever. This quote from our source really hits at home. Because you can always find a new average between any two numbers, it means that in any gap, no matter how small, there isn't just one number or 100, there's an infinite number of rational numbers all packed in there.
And that leaves us with one final fascinating question to chew on. If every tiny microscopic segment of the number line is packed with an infinity of numbers, what does that really tell us about the very nature of the number line itself? What does it say about the fundamental fabric of the math we use to make sense of our world?